Hi, this is Barrett Givens, and in this video, I want to talk about this interesting and useful little lemma about the greatest common divisor of two numbers. So the lemma says, suppose you have three integers a, b, and c, and I should add that they're non-zero, and you have a fourth integer such that a is equal to bx plus c. In that case, then the GCD of a and b and the GCD of b and c will be the same. So let's walk through the proof of why this is true. Okay. So the first thing to notice, and kind of the thing that makes this whole thing work properly, is that the original equation, it gives a in terms of b and c. A is equal to bx plus c. So I have that. But also I can solve this for c. C is equal to a minus bx. Now I can't solve it for b. I would have to divide by x, and because this is in number theory, we're trying to keep everything as integers, but I can solve for c. Okay? So because I can solve both of those that way, because a is equal to bx plus c, that tells me that any divisor of b and c also divides a. Because I could take the divisor of b and c on the right-hand side, I could factor it out of the right-hand side and see that a was equal to that divisor times something. But similarly, by thinking of it as c equals a minus bx, I can see that any divisor of a and b is also a divisor of c. So now that tells me that every common divisor of b and c, it divides A, but it's also dividing B because it's a common divisor of B and C. So every common divisor of B and C is also a common divisor of A and B. And similarly, every common divisor of A and B is also a common divisor of B and C. And putting that all together, what we see is that the collection of common divisors of A and B is the same as the collection of common divisors of B and C. The whole collection of all the common divisors of these two numbers and then all the common divisors of these two numbers, they're exactly the same two collections. And so you have two different sets that are exactly the same. Well, the greatest common divisor is the maximum one in those two sets. And so since they're the same sets, they have the same greatest common divisor. And so therefore they have the same greatest common divisor. So the greatest common divisor of A and B is the greatest common divisor of B and C. All right, let's just see two examples of kind of how this might be useful. So one of them would be something like this. Let's say I wanted to find the GCD of 90 and 25. Now, that's not that hard. I could probably do it, but maybe I can't do it right off the top of my head. So what I can do is I can say, well, I'm going to take any multiple of 25 and add it to 90, and I would still get the same GCD. So I could like do 90 plus 25 times 1, or I could do 90 minus 25 times 2. Okay, I could do anything like that. What I'm going to do is I'm going to do 90 minus 25 times 3. And by the lemma, those are the same GCD. Okay, I've written this is my value of C right here, really. 90 minus 25 times 3. This is my new value of C. Okay, and then this comes out to be the GCD of 90 minus 20 or 90 minus 75, which is 15, 15 and 25. And then that's one I can do in my head. 15 is 5 times 3 and 25 is 5 times 5, and so therefore this is 5. Okay? So this is a nice little shortcut sometimes when you have to find GCDs of large numbers, you can sort of reduce it down to easier problems using this little lemma. Okay, another example that might be useful if you're doing a proof in number theory. Let's say, for example, that I want you to see what you can say about the GCD of a number n and 100 minus n. Assume n is between 1 and 100. What is the GCD of these two numbers? And at first you might think, well, it could be anything because I don't know what n is, so it could be anything. And it's true that there's not enough information to uniquely figure out the answer, but still we can say something about it, okay? So what I'm going to do is I'm going to do this trick again of take one of the values and add a multiple of it to the other value. What I'll do is I'll take the first value, multiply it by 1, and add it to the second value. And so when I do that, I get the GCD of n and 100 minus n plus n. And by the lemma that we started the video with, these two GCDs have to be the same. And so what that means is that the GCD of the original two unknown numbers is the same as the GCD of n and 100. And that means that whatever the GCD of the original two numbers is, it has to go into 100 evenly. So that tells me like, oh, it can't be anything that's a multiple of three, for example. Okay. It could only be, um, I could, list all the divisors of 100. It could be 1, 2, 4, 5, 10, 25, and so on. Okay. If you maybe you could imagine a situation where maybe you had some further information, like maybe I tell you, oh, n is odd and not divisible by 25. And then with that information combined with this, you could say, oh, well, then this GCD has to either be 1 or 5, right? And so you can use these kinds of tricks with this lemma to at least kind of get some information about a GCD of two numbers. Okay, so an extremely useful little lemma that we're going to use all the time. And thank you so much for listening.